Once I have the inverse with me, I can now compute the unrestrained displacement. To do that, we need to estimate the fixed end moments. Okay. Let us take two beams in parallel. So, beam AB of span 3 meters subjected to uniform distributed load, which is 20 kilonewton per meter. This is A and this is B. The other beam is BC, which is also fixed at both the ends. Do not bother about the original condition in the problem. For us, the basic element is a fixed beam. So, BC central concentrated load of intensity 40 kilonewton, equally spaced, and this is 5 meters. Okay. And based upon the equations we gave in the last lecture, I can compute MF AB, MF BA and the reactions at A and B, can compute also MF BC and MF CB and the reactions at B and C respectively. So, let us do that. MF AB will be plus W L square by 12, which is plus 20 into 3 squared by 12, which will be plus 15 kilonewton meter. MF BA will be of the same value, but minus 15 kilonewton meter, because of the simple reason anti-clockwise moments are positive. I want to find the reactions. So, for the given problem, it is easy to know that VA will be 20 into 3 by 2, that is 30 kilonewton, which is upward positive. Similarly, VB is also positive. Let us go to span BC. MF BC will be PL by 8, which will be plus 40 into 5 by 8, which becomes plus 25 kilonewton meter. MF CB will be minus 25 kilonewton meter, because this is clockwise and anti-clockwise is positive, and VB is 40 by 2, which is plus 20 kilonewton, because it is upward is positive. VC is also upward of 20 kilonewton. These are the fixed end moments. So, the joint loads will be reversed of this. Let us now summarize this. I have two beams AB and BC. The values are, this is 15, this is 15, and this value is 30, this value is 30. That is what we got from the last slide. Okay. 15, 15, 30, 30. Similarly, this value is 25, this is again 25, and this is 20, this is 20. I need to add this, sum this, make a single beam. Okay. So, let us say this is as usual 15, okay, but this is going to be clockwise 15 and anticlockwise 25, anticlockwise 10, and this is 25, and this upward is 30, and this upward is 50, that is 30 plus 20, and this upward is 20. This is my fixed end moments, it is not the joint load, please understand. Now, I want to create the joint load. I draw the beam. Okay. Let us create the joint loads by reversing it. So, anti-clockwise, so make it clockwise, 15 kilonewton meter. Anti-clockwise, so make it clockwise, which is 10 kilonewton meter. Clockwise, make it anti-clockwise, 25 kilonewton meter. Upward, so make it downward, 30. Upward, make it downward, 50 kilonewton, and upward, make it downward, 20 kilonewton. So, this is my joint load. Okay. Now, let us compare this with my standard convention what I had. So, the joint loads are clockwise 15 kilonewton meter, clockwise 10 kilonewton meter, anti-clockwise 25 kilonewton meter. This is downward 30 kilonewton, this is also downward 50 kilonewton, this is downward 20 kilonewton. Let us compare this with our standard and enter the joint load vector. The joint load vector will have 6 rows and 1 column. The degrees of freedom are 1, 2, 3, 4, 5 and 6, out of which there is a partition at, okay, because these are unrestrained degrees of freedom and these are restrained degrees of freedom. Okay. So, I call this vector as joint load, unrestrained. I call this vector as joint load restrained. So, if you look at the degree of freedom 1 from this problem, 1 corresponds to the rotation here, 2 corresponds. So, 3, 4, 5 and 6. So, same logic here, 1 corresponds to this anti-clockwise. So, I should say minus 10. Okay. The minus is because if you compare, this is clockwise joint load, but original convention is anti-clockwise. Okay. So, minus 10. Similarly, this is anti-clockwise, the original is also anti-clockwise, therefore, we can say it is plus 25. Okay. 3 by that logic will be minus 15, 4 will be minus 30, 5 will be minus 50 and 6 will be minus 20. Okay. You can compare if you want, we can also draw that particular beam here for our understanding and mark the degrees of freedom. This was theta 1, this was theta 2 unrestrained, then this is theta 3, this is 4, this is 5 and this is 6. So, these 2 are unrestrained and these 4 are restrained. So, this is clockwise, but unrestrained anti-clockwise, so minus 10, anti-clockwise plus 25, then clockwise, but this is anti-clockwise, so minus 15, upward, but this is downward minus 30, upward, this is downward, so minus 50, upward, this is downward minus 20. So, I have this. So, now I can write the J L U vector, that is unrestrained vector, is minus 10 and plus 25, correct. Once I have this, I can now say the joint load displacement of unrestrained will be K U U inverse of that of J L U. So, K U U inverse, if you see, we already worked out that it is with us here. This is my K U U inverse, okay, this is my K U U inverse. I will just rewrite it there, which will be 1 by 1.546 EI, okay, multiplied by 0.8, 0.4 minus 0.4 and 2.133 and this should be multiplied by the unrestrained joint load vector, which is minus 10 and plus 25. So, minus 10 plus 25. Okay. So, I get the unrestrained, which is theta 1 and theta 2, which will be equal to minus 18 by 1.546 EI, and this theta 2 is going to be plus 57.325 by 1.546 EI in radians. Okay. So, we have solved this problem for theta u, but we have to find the end moments, that is important. Okay. We have only solved the unrestrained displacements. May I ask you a question, what will be the vector of restrained displacements, which are, what are the restrained displacements in this problem? Theta 3, delta 4, delta 5, delta 6. What will be this? Theta 3, delta 4, delta 5, delta 6. What will be this vector? Because these are restrained degrees. So, as you correctly guessed, it will be 0. Okay. So, there is no need to work out that. Now, our next job is to find due to the loads, end moments and shear. That is the last step. The general equation is, for finding end moment of ith beam, we have to say K I and displacement I plus fixed end moment of I. So, let us expand this for AB. So, M AB, which will be 4 by 4, which will be K of AB, which will be again 4 by 4, and displacement vector of AB, which is 4 by 1, plus fixed end moments of AB, which is 4 by 1. So, this will be 4 by 1. So, what will be this value for AB? So, let us again draw the problem. This was the original problem. So, these were the degrees of freedom, theta 1, theta 2, theta 3, delta 4, delta 5 and delta 6. Okay. So, for MAV, the values will be, this is A, this is B and this is C. Okay. MAB, the values will be, as you correctly guessed, is going to be M3, that is corresponding to this, M1 corresponding to this, shear 4 corresponding to this, shear 5 corresponding to this. Okay. This is for AB. I have to multiply this with K matrix of AB, which already we had. You can see here K matrix of AB and K matrix of BC separately. I am just rewriting there. So, K matrix of AB, which will be 1.333, 0.667, 0.667 minus 0.667, 0.667, 1.333, 0.667 minus 0.667, 0.667, 0.667, 0.445 minus 0.445 minus 0.667 minus 0.667 minus 0.445 and 0.445. This is for the beam AB, and I want to now multiply this with the displacements of AB, which will be theta 3, theta 1, delta 4 and delta 5, plus the fixed end moments of the member AB. We also already have this here, fixed end moments of the member AB is available here. Okay. So, we can directly write those values there. I am just doing it here. It is going to be plus 15 minus 15 plus 30 plus 30, this fixed end moments of AB. So, simplify this, but the question is this matrix is known, this vector is known, I have to estimate this vector, what happens to this vector? Very interesting. Theta 3 is 0, okay, delta 4 is 0 and delta 5 is 0 and theta 1 is known, you can see here theta 1 is known. So, substitute that value here, the value here and multiply, process it and get the vector AB, which will be actually equal to, I write the values here, 7.234 minus 30.52, 22.234, 37.766. That is for AB. Similarly, I can do for BC. So, I can do for BC. I again draw the problem. This is theta 1, this is theta 2, this is theta 3, this is delta 4, delta 5 and delta 6. This is A, this is B and this is C, okay. This is BC. So, let us do it for BC. MBC will be actually KBC delta BC plus fixed end moments of BC, okay. MBC will have a vector which is 4 by 1. What will be the values? M1 corresponding to this, M2 corresponding to this, okay. Which should become 0 because it is simply supported end, and V5 corresponding to this and V6 corresponding to this, which will be equal to KBC. We have the stiffness matrix of BC, I am writing it here, we already derived that. So, I am just writing it here. This is for the span BC and this will be multiplied by delta BC, which will be equal to theta 1, theta 2, delta 5 and delta 6. Add this to the fixed end moments which we already have for the span BC, which will be 25 minus 25 plus 20 and plus 20. So, very interesting. Delta 5 and delta 6 are 0 because they are restrained, marked in red also. Theta 1, theta 2 are already known to us. So, substitute here, get the value and you will see that that value will be actually equal to 30.517, this becomes 0, 26.105, 13.895. Okay. So, let us plot these values. So, span AB subjected to a load of 20 kilonewton per meter, span BC subject to a central load of 40. So, we said let us write down the values of the vector. The original beam problem was like this. This was theta 1, theta 2 and this is theta 3 delta 4, delta 5, delta 6, and this vector, if we look at this vector AB, this is 7.234 and so on. I am just marking them. So, I am copying this vector back again here. So, 7.234, I am marking this vector here. This is MAB, 7.234 minus 30.52, 22.234 and 37.766. That is what we have here. Okay. Then BC, we have this vector, I am just rewriting it here. MBC is actually equal to 30.517, 0, 26.105 and 13.895. Okay. Keeping this, let us now superimpose these values in the original figure. So, now this is plus, so this is going to be anticlockwise 7.234, this is minus, so clockwise 30.52, this is positive, so upward 22.234 and this is upward 37.766. Similarly, for this positive, so anticlockwise 30.517 and this value is 0 and this is upward 26.105 and this is also upward 13.895. Okay. So, let us superimpose this. Interestingly, you will see that. Let us check this problem, right. I can even remove this figure. Okay. This figure is actually not required at this moment now. Let us check the span AB. So, checking the span AB, the total upward force is actually 22.234 plus 37.766, which is actually equal to 20 into 3. Okay. 60 meters. So, it is checked. If we take moment about this point, okay, moment about A. So, moment about A will be 20 into 3 into 1.5 plus 30.52 minus 37.766 into 3, which will give you 7.234 anticlockwise, which is also checked. If you look at span BC, you see MC is 0 because it is simply supported. Okay. So, the reaction 26.105 plus 13.895 is actually equal to downward reaction of 40. So, it is checked. Okay. If you take moment about this point, that is MB, which will be equal to 40 into 2.5, because this span is 5 meters, 2.5 minus 13.895 into 5 will be exactly equal to 30.52, which is here. And you will also see that these reactions are matching, 30.52 clockwise, 30.52 anticlockwise. So, finally, I have a beam which is solved which is my summary for this load and for this load. The reactions are 7.234, 30.52, 22.234, 63.871, 13.895, because this value will be the sum of these two reactions, Okay. So, that is the whole problem which has been solved, and this loading is 20 kilonewton per meter and this is 40 kilonewton, this is 3 meter EI, this is 5 meter EI. The problem is now solved. We can also check this by one more alternative, which we will discuss when we do the next problem. Thank you very much.